Hello, welcome to lesson 16, continuing on with continuous random variables. We're going to look at a very common one here, the normal distribution, or sometimes referred to as a bell curve. So the PDF here is a little bit messy with the mean, mu, standard deviation, sigma. The density function is 1 over radical 2 pi times sigma e to the minus x minus mu squared over 2 sigma squared for all real numbers x. If we make a substitution, z is equal to x minus mu over sigma, this will alter the situation so that the mean becomes 0 and the standard deviation 1. And we're going to prove some of these properties here and then extend back to the general case. So we're going to work with this simplified density function based on the substitution. Z is equal to x minus the mean divided by standard deviation. This creates a normal random variable with mean 0, standard deviation of 1. So we'll work through some of that. So first up, we're going to prove that the expected value, the mean of this new variable, is 0, that the mean is 0. So we're going to do z times the density. I know we're using x here instead of using z instead of x because we made the substitution, but same kind of process here. Integrating from negative infinity to infinity, z times f of z dz, which is z times the density, 1 over radical 2 pi e to the minus z squared over 2 dz. And we want to show that this ends up being 0. Now, you can do this by integration by substitution. So this is a little bit quick, but the situation here is that if we know or believe that this will converge, we have symmetric limits here and an odd function. So the integral will basically cancel out to 0. But you can do a u sub here. You would have to deal with the infinite limits, but you can do a u sub of negative z squared over 2, and the derivative will line up nicely with the z out front there. Now, up next is to prove the standard deviation is 1. The standard deviation of this new variable z is 1. So first step we have to do is compute e of z squared, the expected value of z squared. So it's z squared times the density. So here, u substitution's not going to be very helpful because the powers are the same. So we're not going to get that derivative lining up here. So we integrate from 0 to infinity and then double. Because we have these square terms here, this function is symmetric over the y-axis. So we can do half of it, 0 to infinity, and then just double. Improper integral infinite limit, we write it as a limit as b goes to infinity of the integral 0 to b. So I have to do a little bit of creativity here. We're going to break apart z squared as z times z, and then we're going to use integration by parts on this. Sorry, just trying to line this up here. All right. So we can't really use the regular rules of integration by parts, but What's happening here is that the z portion has a nice derivative of just 1, and then this expression we can integrate with a u substitution. With the integration by substitution, making the substitution the exponent, negative z squared over 2, works out nicely here. So let me just write that in a little bit here. So we're gonna make the u z, and then everything else here is the dv. So now we're just working with this piece here, trying to integrate ze to the negative z squared over 2 dz. And so the method here is to do a u substitution to make w equal to, I'm using w because we already have a u in the problem, and we make w equal to negative z squared over 2. And then the derivative of that is negative 2 z to the first power dz over 2. And then the 2's cancel out. So we have a negative sign there, but it's very close to matching with the z dz we have there. And so the antiderivative will end up just being the exponential function times the minus sign, technically divided by the minus sign. So that gets us to v. So doing the uv minus integral v du, u is z, v is negative e to the negative z squared over 2, minus integral of v du is the negative e to the negative z squared over 2 times just 1 dz. And the double negatives cancel out here to a plus sign. All right, so we're taking the limit as b goes to infinity on this expression. And we do have the constant there, 2 over root 2 pi, 2 times 1 over root 2 pi. So even this is a little bit messy. Certainly this is beyond the scope of anything I test you on, but just want to give an idea of where this stuff is coming from. You have to do L'Hopital's rule on the first expression to get a limit of 0. If b is going to infinity here, we have a negative infinity term here. We have e to the minus infinity, which is 0. So you have a 0 times infinity situation there. You have to do L'Hopital's rule. In the second portion here, we're using the fact that this is a density function. Now, we never actually did the proof here, but if we believe that we have a density function here, if we believe this is a density function, then the integral over the whole domain, which are all real numbers, has to be 100% or one whole. And so that's how we arrive at the 1. This portion here is a density function together with its multiplier out front. So that's 1. And then L'Hopital's rule on this expression will give us a 0 when b goes to infinity, and when you plug in 0, you will also get 0 there. So L'Hopital's rule, and then the density function rule here to get this second portion here. Okay, so if you believe all that, and again, I'm not expecting you to be able to do this on an exam, then the variance formula is expected value of z squared minus e of z quantity squared. So expected value of z squared is 1. The mean was 0. 1 minus 0 squared is 1. We end up with a variance of 1 and a standard deviation. Take the square root, it's still 1. All right, we made a substitution way back there. We use z equals x minus the mean over sigma. I'm using y here, but essentially it's the same idea. So we want to go backwards here. We want to go now from the special case of z where the mean was 0, standard deviation 1. Now we want to go backwards to the original format. And we can do some algebra here to solve for y. If you cross multiply, you get z times sigma plus the mean. The expected value of this expression using the linearity here, it's like expected value of ax plus b. Sigma is a constant that'll factor out times expected value of z plus the constant mu. Now, e of z is 0, so this drops out, and we do get a mean of mu. So I know we always use that for the notation here for the mean, but the idea is that we're kind of justifying that this formula is correct and that this symbol here, it really is the expected value or mean, and the sigma here is the standard deviation. So we got the mean to work out. Now we have to do the standard deviation. And again, we're going to use the variance here because the variance has the nicer property. So we'll work with the variance first. The variance of ax plus b, remember, adding a constant doesn't affect the variance. Variance is measuring spread. So shifting the data doesn't matter. So this adding mu doesn't do anything. The scalar multiplier here, this coefficient sigma, comes out as sigma squared. So it's sigma squared times the variance of z, sigma squared times 1, variance is sigma squared, standard deviation is the square root. And so we do end up where we want it to be, where the general normal um, random variable, the expected value is the mu symbol, and the standard deviation is sigma. So this is the graph here for the standard normal, mean 0, standard deviation 1. So notice it's bell-shaped, it's symmetric, the mean, the median, the mode, all the same here. Mean is 0. And it looks like a bell. We have, a large portion of the probability is centered near the mean. All right, so this is our density function here for the special case normal random variable mean 0, standard deviation 1. And then the cumulative distribution function, remember, that's the probability of being less than or equal to a given value. It's going to be the integral. Remember, continuous function, we're integrating up to that specific value. It's integrating from minus infinity to the given value. That is the CDF. Now, this integration here is difficult. I put that in quotes. It's impossible to find an antiderivative in a closed form for e to the minus x squared. There are certain other techniques, power series, and other things, but in terms of calculus 2 integration techniques to find an antiderivative, it's impossible. Power series from calc 2 would work. So what we have here is there's a table of values here that we use for this. And the table is set up basically as giving the area to the left or the cumulative less than or equal to situation here. So typically here, when we have a z value, it's going to be to 2 decimal places here. And so we use up to the 10th digit we get from this row, and then the second digit, the 100th digit, we get from the column, and then we can read off the area. and that the decimal in the body of the table, that's telling you the area to the left, the probability of being less than or equal to a given z-score. In the next video, we'll go through some actual examples here.